Hey, hello everyone. Welcome to this seminar by GRSS, in particular by the Geoscience Standards for Earth Observation Technical Committee. Today, the title is the CIMR, Copernicus Imaging Microwave Radiometer. The speaker is Dr. Donlon. Dr. Donlon received a PhD in oceanography from the University of Southampton, UK in 1994. Later, he worked at the University of Colorado, USA as an assistant research professor at the European Commission Joint Research Center, Italy, for 5 years in the Institute for Environment and Sustainability, and at the Met Office, UK, for 5 years in the Operational Oceanography Division. Dr. Donlon joined the European Space Agency STEC in the Netherlands and in 2008, and he is currently the head of the Earth Observation System Architecture Office. So now we can start the meeting. So I will. Okay. So now, Craig, the floor is yours.
Okay, if you pop it into, I guess, yeah, there we go. Thank you for the introduction. Yeah, I'm speaking on behalf of a variety of people working on the Copernicus Imaging Microwave Radiometer mission, and they're all part of the project and science team at the European Space Agency. I work over in STEC, which is the European Space and Technology Research Centre, a sort of JPL, if you like, style of work for ESA. And next slide, please. Okay, so the starting point for this satellite mission is really where we are with global warming. And we can see here just a simple graphic that shows, okay, our Paris Agreement should be about plus 1.5. We're approaching that already. So once we start warming beyond that, we're in trouble for climate policies and even the sustainability of our societies as we know it. But we know that this is done through human influence. Next slide, please. Hugo, can you pop the next slide? There we go. So in the Arctic, which is where we have a big focus, although our mission is global, Arctic amplification and its intensification is something that's well documented from space. I mean, starting on the top right with carbon dioxide warming the planet, working through heat fluxes, sea ice melting, albedo feedbacks, flux feedbacks, thermospheric contributions to sea level rise, as you can go around the circle. This is a vicious circle of change, and there's no wonder that we see from space today an accelerated warming and the impacts of that in the Arctic regions. So our job really is to make sure that we can provide documented scientific evidence, measurements, that is, to underpin policies, support the implementation, monitoring, and the outcomes of those policies. Next slide, please. So when we started this mission about a decade ago, well, actually we started about 20 years ago, but a decade ago for sure, the landscape of microwave multi-frequency imaging radiometers was not particularly wonderful in Europe. We had the MWI instruments, which are on the METOP satellites, the multi-frequency imaging capability. It's a conical scanner, but they didn't carry any of the low-frequency measurements that we really need to provide continuity to missions like the AMSA-E, AMSA-2, and AMSA-3, which should be launched this year. Also, L-band were giving us access to salinity and soil moisture. In ESA, we have the soil moisture and ocean salinity mission, and in the US, the SMAP mission, building on Aquarius. And what we wanted to be able to provide was CIMR in continuity. And you can see in the left figure there, we had a very optimistic view of being able to launch in 2026. Next slide, please. So CIMR is really coming from a set of user requirements set up by the European Union and the European Commission. They tasked a group of independent scientists to review what new satellite missions were required for the Copernicus program, which is the operational satellite program of the European Union. And as a priority, a passive microwave radiometer mission was considered as a priority for this Polar Expert Group's second report. Because it responded in the best way to all the requirements that were set before the European Space Agency, as documented in these 3 classical documents here. And these are all available on the web if you want to look at them. Next slide, please. one of the drivers for this is, of course, if you take one day of 2 thermal infrared satellites with a 1,400 kilometer swath, the Sentinel-3A and Sentinel-3B SLSTR datasets, this is from yesterday, you can see that there's a huge gap in coverage, just mostly because of clouds, and there's no way out of that. Thermal infrared cannot see through clouds. Next one, please. However, if you move to a microwave approach in the 6.9 gigahertz area of the spectrum, then you can pretty much provide all-weather capability, near all-weather. I mean, in strongly precipitating conditions, we can't really make measurements. But the kind of difference that you see in these two plots taken on the same day is quite dramatic. So we get coverage, and in particular, we get coverage in the high latitude regions, which in the north are just simply not imaged by thermal infrared techniques. And that biases the climate record, as well as leaves us the problem of having no situational information for shipping, safety of life at sea aspects in those regions. Next slide, please. So in Copernicus, we have a series of different policy drivers, which are driving a whole fleet of different Sentinel satellites that are part of this Copernicus program. They're all set here. If you click again, please, Hugo. These support EU policies and what's called a Green Deal, and CIMR is one of those. So we'll review that mission today. Next slide, please. So really, in a nutshell, what we're looking for is to underpin the European Union's Arctic policy, which is really making sure that there is a whole series of activities on climate change, sustainable development, and international cooperation on Arctic matters. And as you know, politically, it's quite a hotbed of a region at the moment for a variety of reasons. As the sea ice is retreating, it becomes more accessible for a variety of different applications, shipping being one of them, but also seafloor mining. And we know already that polar oceans are fundamental to understanding the global environment. And the idea of the CIMR mission is to be ready for an ice-free Arctic by looking at key variables of that regions, with measurements in that zone 60 degrees north or south of every 6 hours, with good 95% global coverage every day. So it should be really a bit of a game changer for Copernicus in terms of its capability. And you can see an image there of the satellite as envisaged today. This data will support then the Copernicus operational services in the atmosphere, the marine, land, climate, emergency, and security domains. And all those services are operational today and are serving many thousands of users every day. Next slide, please. So, I mean, if you think about the Arctic, it's really an ocean covered in ice. It's worth just reminding ourselves of that. And the picture on the right gives you an impression of what the ice really looks like when you're out there. It's not this, the marginal ice zone, it's a very complex environment and demands certain features of a satellite microwave mission in terms of resolution and sensitivity, depending on what you want to see. Next slide, please. And the complexity of this environment is sort of summarized in this little cartoon here. I mean, there are many different processes, and I'm sure that many of you might see some that are missing, but these are certainly some of the highlights of the kind of processes that we really want to try and capture using the CIMR mission. If you just click through a few times, Hugo, please. Fundamental to understanding what's going on here is sea ice concentration, its thickness, its type, its drift. It's the ice sheet melts and permafrost, the sea, land, and ice surface temperatures, the salinity and the soil moisture, the ocean vector winds, which are driving a lot of the forcing over the ocean and the ice, snow depth, snow extent, and snow water equivalent, vegetation, and indices of that, and also the atmospheric side, total common water vapor and liquid water vapor path plus precip. And we can measure all of those in the microwave with careful choice of frequencies and the appropriate resolution, of course. And the idea of CIMR is to really place the Arctic into this global context. How does the Arctic fit together with the rest of the global environment? Next one, please. So sea ice, we know, is declining steadily. I mean, there are ups and downs in this plot, but here's from the NSIGC, and you're probably all familiar with that plot. And it shows a quite precipitous decline in terms of millions of square kilometers of sea ice extent up until 2024 in this case. You can see the difference between 1979 and the minimum in 2016 on the globes there. So this is a key variable and an indicator of change. Next slide, please. And also sea surface temperature. It's fundamental to an understanding of air-sea interaction and a good gauge of many major processes in the ocean. If you click through, please, Hugo. Here we can see the global mean sea surface temperatures derived from the climate data sets. That includes mostly thermal infrared, and also some of the drivers, the solar effects, the volcanic eruptions, the Pinatubo and the El Nino itself. And if you use those together with the Earth energy accumulation, you can find that the patterns fit the SST record pretty well. And this is work of Chris Merchant and others. But we certainly see an acceleration in sea surface temperature rise over the last decade or so. So we know that climate change is taking place, and we need to maintain a capability to monitor that well into the future. And the CIMR lifetime is looking at a 20-year lifetime using 2 satellites. Next slide, please. Another view of sea surface temperature anomalies, the El Nino effect and the La Niñas are extremely important for global climate aspects. Next slide, please. And also local anomalies, which are increasing in terms of extremes. So marine heat waves, and there was one earlier this year off the west coast of Ireland, which I had the privilege to sail through on a sailing ship this year. And these cause a lot of damage to the local environment and in particular its ecology. Next slide, please. Over the land, we can also, well, here's another example from 2 years ago, which is where we had a 5 degree higher than normal sea surface temperature in the North Sea. So significant local marine heat waves. Next slide, please. We can do quite a good job over the land in the thermal infrared. And again, you can see the impacts here where in Italy, we've got temperatures of 50 and Bucharest 45 degrees, which is really unsustainable for most of the people living there. And of course, while those areas are somewhat used to hot temperatures, these are extreme temperatures even for those guys. It's warmer than Tunis and Tunisia. So we have a real threat. And as we move forward into anthropogenically driven climate change, we can expect more and more of these extremes as the system flips into hysteresis, potentially before significant tipping points. We need to be there with space assets to make sure we can monitor what's going on, because this is the way we can provide political leverage to make change. Next slide, please. So our land surface temperature from microwave, we again get an all-weather capability, but it's much more tricky to do this. This is an example from Seville, which is thermal infrared. The point of this slide is to say that there are techniques that will enable us to derive land surface temperatures reasonably well if you start to make good assumptions about the emissivity using thermal infrared. Next slide, please. But in the microwave, it's much more tricky, and we'll come to that later. We can do a pretty good job with salinity, and we have the SMOS mission, soil moisture and ocean salinity, and the SMAP mission from NASA, soil moisture mission, both using L-band capability at 1.4 gigahertz. And there are temperature issues there, but one of the things is sea surface temperature and the salinity go together in terms of understanding the ocean, the thermohaline circulation of the ocean. And when we're dealing with sea ice processes, it's brine that is rejected from the formation of sea ice as it forms freshwater ice. So being able to measure salinity at the same time as sea surface temperature is really important. Next slide, please. Of course, you can use salinity just as you can use sea surface temperature to get a hint of what's going on with El Niños, and we can see a slight leading edge for La Niñas and El Niños in the salinity signal beyond the temperature signal. We need a longer data record to do this, but there is a hint there that the salinity is weakened in the Pacific Ocean prior to an El Nino event, which is quite interesting. But again, we need a longer time series to do that, and it's still tricky to model. Nevertheless, being able to monitor this from space is quite important and provide continuity to the SMOS and the SMAP missions. Next slide, please. Also, in summertime, sea surface temperature patterns can be easily masked by diurnal thermoclines that build in the top meter or so of the sea surface in hot weather, light wind conditions, whereas those don't seem to be the case in the salinity signal. So you can see in panel A there, that's the salinity signal overlaid with geostrophic currents from the Oscar time series in this case. Whereas in B, that's just the sea surface temperature, and you just don't get the same features. They're masked out by this warm layer effect, eventually, which stops you from seeing what's really going on the mesoscale field. So again, using salinity and temperature together is really, really important. Next slide, please. In terms of sea state and storminess, which is a proxy in this case for winds, we can see from a decade of difference, or 20 years in this case, in the CCA Climate Change Initiative data sets, that there is an increased storminess, if you like, in some areas, and we'd like to be able to monitor that. Next slide, please. And to do that, we'd like to be able to retrieve wind vectors from the CIMR mission using HMV polarizations, which I'll come on to later. We can also measure soil moisture, a very important variable for weather forecasting in L-band, but you can also do a lot when you have a multi-frequency capability. Next slide, please. We also want to make sure, keep clicking there. Okay, yeah, together with soil moisture, vegetation parameters are extremely important because they are actually part of the system. And again, being able to retrieve indices, in this case, vegetation optical depth from SMOS in a multi-frequency capability would be very useful. Next slide, please. And of course, snow cover and snow water equivalent, if possible, from microwave. Those are challenges for us. The snow extent is not so much of a problem. Snow water equivalent will remain a bit of a research proposal using the CIMR data, but nevertheless important. And so we'll try to do that as well. Next slide, please. So our objectives for the mission and its aim, I'm not going to read these out, and I just point you to that web link there where you can download the mission requirements document, which sets out the justification and the actual requirements for both level 1 and level 2 measurements, so instrument measurements and then geophysical products. It's quite an extensive document, but that's been the basis of actually building the mission, which is in progress now. Next slide, please. So we didn't start recently. We started about 30 years ago at the European Space Agency. We had several mission concepts, the first one being the multi-frequency imaging microwave radiometer back in 1991. And then we've looked at a variety of different concepts using 1D and 2D interferometers. We've looked at push broom sensors. We've used multi-beam formers, all sorts of different types of antennas and reflectors from parabolic through to these arrays. So we have a lot of heritage in what we're trying to do here. And every time we've done this work, all roads lead to the same result, which is that a conical scanning radiometer with a fixed inclination is the best choice for this kind of measurement system. Next slide, please. In terms of a primary variable CS concentration, we know that the best retrievals are done using a 6 gigahertz vertically polarized approach. Multi-frequency algorithms are not too bad, and then they get progressively worse as you move up in terms of frequency spectrum. But we also know that at 6 gigahertz, we need a very, very, very large antenna, and so we have to make some compromise. The other thing is we want to make sure we have good oversampling, both in the forward and in the scan direction, and also in both a forward and a backward view, like SMAP does. So next slide, please. We know that in terms of brightness temperatures, from 1.4 to 89 gigahertz here, which is really the AMSA frequencies, for multi-year in red, first-year ice in purple, and open water in blue. In the lower frequencies, we have a pretty good, reasonable separation between open water and the ice. As we go up in frequency, these tend to mix quite dramatically, and at 89 gigahertz, it's not that easy to separate these things. So for good sea ice, we really need to have these lower frequency, but we also need the high resolution because sea ice is very complex. Next slide, please. For sea surface temperature, we've looked at a variety of different approaches, different channel combinations, and looking at their Jacobians. And what we see is, of course, that the 6, 10, 18, and 23 gigahertz are really pretty good. 6, 10, and 18 themselves probably gives us the best results for a standard deviation. We hope to improve on that by making sure that our mission has very low noise equivalent difference temperatures. Next slide, please. For salinity, there's a very clear temperature dependence on the ability to retrieve salinity, which is a challenge for us in the Arctic because it's cold. And so again, this directs us to say that we need very, very good sensitivity in the L-band channels. And we also need a third Stokes parameter here to accommodate for Faraday rotation in this band, also a little bit at C-band, but definitely at L-band. So this drives the performances that we need to retrieve a good salinity in the Arctic. Just for your background knowledge, both SMOS and SMAF have noise equivalent difference temperatures, so sensitivity is around 1 to 1.2 Kelvin. So we're really pushing what's possible here. Next slide, please. In terms of sea ice thickness, we know that from SMOS and from SMAP in both V and H up to a thickness of around about 0.2 to up to around about half a meter, we have some sensitivity, and that sensitivity is frequency dependent in terms of thickness. But we would like to make sure that we have polarized brightness temperatures and multi-frequency to capitalize on this to make some thin sea ice thickness retrieval, so at the ice edge, which we've done before. If you click the next slide, SMOS has a time series now of thin sea ice and sea ice from space. Next slide, please, Hugo. I don't think the animation will go very quick, but there's a little animation there which shows how the sea ice is thinning. And here we see the SMOS offset against NSIDC extents up until, I think, 2024. And you can see around the edges, we can do a reasonably good job with microwave radiometry. Next slide, please. In terms of wind, we need good polarized measurements with full Stokes, so H and V in the third Stokes parameter. And what you're looking at here on the left is the Sentinel-1A SAR, which is wind at 1 kilometer. And what we expect at 60 kilometers, and that being a measure of the projected ellipse on the surface of the Earth by taking the average of the maximum and minimum ellipse dimensions. So you can see it's pretty blurred, but if we mix them with C and X band, we can do image sharpening quite well, and we get a good result. Next slide. If you then add the polarization, click again, please. You can see that we can improve things quite well. Next slide. Yeah, so we actually sharpen, and if we add then the Stokes parameter, we can get a direction, so we can get a wind vector. And this would be for winds over about 5 or 6 meters per second. Next slide, please. We also know that looking at the differences between WindSat, which has one look, and what we expect from 2 looks, forward and backward view look on CIMR, that we can expect to do some improvements. So we're looking forward to pushing that. This is work with Thomas Meisner and Luca Ciaricadilli over at Remote Sensing System with Frank Wenz. Next slide, please. We know that this approach works when you compare the SMOS-derived L-band wind speeds to the scanning multi-frequency microwave radiometer wind speeds, which we take as truth from hurricane flights. We have a reasonably good overlap. The differences are largely due to the spatial footprint on the ground of the SFMR instrument and the SMOS instrument itself. But there's a good correlation here, certainly enough to actually warrant use in operations. So next slide, please. We're trying to make sure that we capitalize on other missions. So we're flying in the same orbit as METOP SG-1B, except we're just rotated to a 6 a.m., 6 p.m. dawn dusk orbit. What this does is it sort of interleaves the 2 satellite ground tracks, but over the pole they're only separated by plus or minus 10 minutes. So in the Arctic regions, the Antarctic regions, we get pretty good overlap, which is quite beneficial for the winds. Next slide, please. We can also use the e-folding penetration depths or depths of emission at different frequencies. This is work with Andreas Colliander at JPL to study the water properties of snow and ice, and particularly in Greenland, if you click again. So the snow wetness and actually where we're getting drainage from over Greenland. Next slide, please. Andreas has done quite a bit of work to try and simulate what we can expect from subsurface melt in C-band and frozen subsurfaces in KU band around the Greenland ice margin. So we're looking forward to actually working with CIMR on that. Next slide, please. Okay, so how do we select the channels? I mean, maybe some of you are familiar with this classical figure from Willite in 1979. And we always wondered if that that negative Jacobian in sea surface temperature was true, and could we exploit it? So we did some work with Lisa Killick. If you click again, please. And Lisa remodeled all of this, and unfortunately that doesn't hold, and we get a pick up again. But this diagram for temperature, salinity, wind, sea ice in different atmospheres allows us to set where we want our primary frequencies: 1.4, 6.9, 10.65, 18.7, and 36.5. And there's a technical note on that if you're interested. It's quite nicely done. Okay, next slide, please. So sea ice spatial characteristics are complex. Some photographs and an image from Sentinel-3 in the AVHR top right there, which show you the complexity. So 10 meters resolution bottom left and about a kilometer top right, but a bigger area. So we need to improve the resolution of conventional microwave radiometers. If you click the next slide, please. And when we compare, oh yeah, this is taken from an aircraft as flying just over the east coast of Greenland. And again, you can see the complexity. I'll click through again. So in order to get at this, we really want to improve the instantaneous field of view. So we're looking here at the -3 dB projected footprints on the ground. And we have this footprint size that we define, which is the major and minor ellipse dimensions projected on the Earth divided by 2. It gives us a linear distance to compare different satellites. And CIMR is shown in yellow. In magenta, it's the microwave imager from METOP, and the AMSO2 is shown in orange. So in all cases, except for the L band, we're really trying to have a bit of a leap in capability in terms of spatial resolution. But in order to do so, we need a very large antenna. It has to be greater than 7 meters in diameter, which leads us to a mesh technical solution. Next slide, please. But the impact of that, if you control the beam characteristics very well of your antenna, then if you compare what we expect from CIMR to AMSO2 here in the Baltic Sea, which is a bit of a challenging area, we have a much better coverage. Next slide. And when we go to sea ice in that same area, it's the same story. So much better performances, which is exactly what the Ocean Sea Ice Satellite Application Facility and the NWP and Numerical Weather Prediction Centers want. Next slide, please. We're also doing quite a bit of work on standard total uncertainty allocations, and this is the calculation we use to give to industry that are building the spacecraft. So it's not necessarily a full scientific breakdown. What we told industry is, okay, if you can give us a stable noise equivalent delta T temperature, plus you give us an orbit stability and a lifetime stability, we'll give you back a pre-launch calibration coefficient that you can play with. And if you play with that by optimizing your pre-launch on-ground calibration, we should have a good system. And that's what they're working to at the moment. And these are the figures that we've allocated. So they're very stringent. It's a big challenge for any industry to meet these, but I'm happy to say that at this moment in time, at the end of phase C, just going through the CDR now, these performances have been largely maintained. Certainly the NE delta Ts. Next slide, please. The other thing we have to deal with is radio frequency interference. And you can see here from small to L band how the RFI has evolved. It's got less here. Actually, in the last 2 years, it's got dramatically worse because of the various wars around the world. So we can do something in terms of reducing the RFI, but we can't actually get rid of it. It's always going to be there. And so we want to make sure we've got an onboard system that will actually detect and to a certain extent mitigate RFI. And I'll discuss that a little bit in a minute. Next slide, please. Okay, here's the mission performance requirements. I'm not going to dwell on those. They've sort of been presented. So we'll take the next slide. Okay, so the system itself includes two satellites, CIMR A and CIMR B, which will be launched sequentially, and they'll be using a Vega C launcher. If you just click through a couple of times, Hugo, the different centers of ESA. So Karuna will be the main receiving station, ESOC will be controlling the satellite, and Esrim will be producing and responsible for the ground segment activities. Next slide. Oh, Svalbard also we use for downlink. So just click through a bit. Next one, next one, next one. Next one. So you get an idea of how large this satellite is. It's 14 meters high with a reflector of 8.6 meters in diameter. So it's a big beast. The solar array spans 6.4 meters, and we're using a 3-axis stabilized platform. And the top part, the instrument crate as we call it, with the antenna and the large deployable reflector, that rotates at a rotation rate of 7.8 revs per minute. Next slide, please. It's 2 tons in total. If you just click through, Hugo. It's a conically scanning total power radiometer with this large deployable reflector. It's highly integrated in the top part, the instrument part, the crate as we call it, with a 700 kilo mass, including margins. It's about 920 watts of power with 50 receiver channels in total, about 11 gigahertz of total bandwidth. Next slide, please. A little bit of background on the spacecraft. I'm not going to go through that, only to say that we have 7 years design lifetime, but we have consumables on board for 12.5 years in operations after 6 months commissioning. So we're really expecting this thing to last longer than the 7 years design life. Next slide, please. Okay, a little animation. You might have to click one more time, I think, just to make it go. I don't know why it holds up here. Oops, try again. Sometimes you just have to click the animation bit and it starts again. If you click in the animation bar, somehow it just starts. I don't know why it gets stuck. Yeah, just click in the bar. In that bit, yeah. There we go. So what it's doing is it's scanning multiple feeds, and the feed arrays are set up at the top left-hand side. You can see we have multiple K feeds. We have 8 of those, and we have dual C and X band feeds, 4 of those, and 1 L band. And as we scan, we sample multiple lines at the same time, and you can see here that there's a slight offset in observing zenith angle on the L band, and that's just to improve the footprint size on the ground. Next slide, please. We have a rotation rate of 7.8 revs per minute and a 1900 kilometer swath with an altitude of around a design altitude of 830 odd kilometers. So the F over D is about 8.858, which is quite good. With an 8-meter antenna, that gives us an aperture of around 7.13. So it's quite a challenge to build this, and it's a deployable mesh antenna, but I'll come on to that in a second. Next slide. The way the imaging is made is there's about a 58 kilometer overlap in the L band, a 15 kilometer overlap in C band, and the Ka band is just more or less tangential. We are lacking 1 feed. We would like an extra feed to meet Nyquist, but it wasn't possible to accommodate that on the focal plane array. You can see the focal plane, which is on the bottom right there. We're using an integrated patch antenna for the L band. Next slide, please. Okay, I've discussed this a little bit already, but here's a different view of how METOP and CIMR will phase. They're on exactly the same orbit, so we have to have very stringent orbit control. Otherwise, these two spacecraft are going to hit each other. So we have to maintain very stringent requirements at the equator crossing time. So there's an active control of the spacecraft orbit all times. Next slide, please. But with this configuration in the Arctic zone, in the Arctic region, we'll get about 8 passes. And you can see here the number of revisits in 24 hours. So in the high Arctic, we're up to 8 passes a day. So this is quite a spectacular amount of coverage. The inclination is very, very high. So we have no hole at the pole. Next slide, please. And this is shown here. L-band, we have a very small hole of about 1 footprint size, so about 60 kilometers. But at C-band, K, Ka, we have no hole at all. So we have full Arctic coverage. Next slide. The system itself is fairly classical. It's got an antenna front end. It's got a receiver, a radio frequency processing unit, and the control electronics, which then interfaces through a scan mechanism, which is using roll rings to provide data and power. And the instrument control unit is in the fixed part of the satellite. So there's two parts. The instrument sits on both the rotating side and actually on the spacecraft static side, if you like. Next slide, please. The rotating crate itself is made up of two parts. It's got an RF module, which then sits on top of the service module. And if you click again, the complexity of integrating all this is pretty challenging, with 50 different receivers, then leading all of the various waveguides. Is a bit like constructing a sort of Star Trek kind of engine, if you like. And it's very difficult to actually integrate. And the first couple of designs looked great on paper until the integration engineers came along and just said that it's impossible to build that. You're going to have to redesign it. So we're quite happy with the design now, and it's pretty stable. Next slide, please. In terms of the deployment of the reflector bundles up into this little basket in a sort of classical way, and the reflector itself only weighs 53 kilos. It's deployed in 3 different sections on an arm that's first deployed upwards, and then a sort of a basket of the antenna itself is then folded upwards, and from that part, it's tensioned to actually deploy the antenna in its full glory. So all in all, it takes about 30 minutes to do this, but I'm sure that will be a very nerve-wracking 30 minutes when we're all watching. Next slide. So just click through here, just keep clicking through. So we've done a lot of pre-developments, or we've done several pre-developments and tests with new antennas, especially looking at different mesh types, which have been quite challenging, but we've now got a good mesh of 20 micron gold molybdenum wire. And we have, if you click again, an engineering model which is now being qualified actually for a first version of the reflector shown in the top left there. So it's quite a thing of beauty when you actually stand in front of that. And unlike most conventional spacecraft engineering, this thing is somewhat a piece of art in its own way. And you can see the white bands are actually providing the shape of the antenna, and the gold mesh is then sitting on actually beneath those white stress and forming webbing. Next slide, please. The in-flight calibration, obviously with an antenna this big, a reflector this big, it's difficult to put hot and cold loads on the spacecraft. There's just not enough room. So what we're using instead is a switch to switch between a hot load internally and an active cold load, and we're modeling the front end of that from the reflector down into the receivers. And if you click next slide, there are 50 of these calibration devices, but we can actually choose where we want to put the calibration in the scan. We have up to 16 locations that we can choose. And what we do is actually use a thing called flip cal, where we calibrate on either side of the swath, because we're so oversampled in between that we're able to recover the lost data from calibrations on subsequent scans. So this is quite a nice approach. Next slide, please. Those active cold loads are pretty stable, and you can see in the bottom left here there are 3 of them there which more or less overlap, and this is nearly a month's worth of data, I believe. And the stability of those is they're all moving at the same across the same excursions, which is due to the local environment and test setup, but it gives us a very fine performance of plus or minus 0.1 Kelvin, which is traceable then back to SI by the calibration of these curves on ground. Next slide, please. It's complemented by deep space views, by the way, as well, to give us a reference point. If you just click through these next 3 slides, they're really to show that the RFI at 1.4. Next slide. and at 6.9 and 10.65, mostly due to TV broadcasts reflected at the sea surface. And the next slide, at 10.65, has been modeled by CIMR, and you can see the impact of broadcast geostationary satellites, both sort of now and in the future. Next slide, please. Next slide, please. And what we're doing here is we've got our subsystem, we've got a conventional receiver setup with preamps, frequency converters, channel filters, and local oscillators to control our analog feeds. And we're feeding those after down conversion into C-band into FPGAs on board. We have 7 FPGAs on board to process and detect and mitigate RFI signals. Next slide. And the way we do that is we use the classical approach where we have several algorithms working on subbanding in both time and frequency to detect continuous wave and pulsed RFI signals. We then remove those elements from our data set and reconstruct on board the new data set with a new NAD delta T. So we send the original data plus the clean data down to ground. Next slide, please. Next slide, yeah. So we have this thing called on event mode. So when we detect RFI, we actually reconstruct the data on board, and we send that to ground where it will be used as part of the ITU work to report on RFI at C-band, L, X, K, and KU. So for the first time that we actually have all of these channels actively detecting RFI on board. The degree to which we can mitigate depends very much on how well these the time frequency matrix can be resolved on board, but we're quite confident we can do a good job. Next slide, please. Okay, if you just click quickly through these, yeah. I mean, in terms of who's responsible for what, ESA is responsible for the instrument, the payload, the spacecraft, so its ground control and production of level 1, and all of the products in the land and the polar regions. And EUMETSAT will be then working on the global ocean and atmosphere products. And both agencies will be working together on the CalVal aspects. Next slide, please. We've got an open science approach. All of our software, including the ATBDs and tools, we've got our open source. And actually, there'll be a product algorithm laboratory that's been set up now. And we have a big fostering of the science community, both in the US and also in Europe. Next slide, please. I'm not going to go through this, but just to show that, you know, we're producing level 1A, ungridded instrument geometry in counts, and also level 1B data sets ungridded in the instrument geometry as input then to gridding procedures that allow us then to process up to level 2 geophysical parameters. And the reason we do that is every geophysical parameter has a different choice on how they want to do the regridding. And to help, we've produced a dedicated fast toolbox which allows to regrid some of the data very effectively in operations. Next slide, please. All the ATBDs are online. They're done in Jupyter book format, so it's very easy to
We cannot hear you. I cannot hear you, Craig.
Okay.
Now, yes.
Am I back?
Yeah, thank you.
Or not?
Yeah, I can hear you now.
Hello?
Yes, I can hear you.
Hello, anybody? Anybody there? We can hear. Okay. Well, if you can click the next slide, I can't see it. But oh, there we go. It's coming back. Yeah. We've done a lot of work on uncertainty modeling. Just click through this, please, Hugo. In terms of both the random components, the systematic.
We cannot hear you, Craig. Now,
Oh, dear me.
yes, back.
I can try this one. Oh, this one. You can hear. Okay. It says you can hear. Maybe this is better. Are we back?
Back?
Yes. Okay. Maybe you can click through. I don't know if it'll keep going. We're more or less at the end. Or we could, I mean, we can even stop here, actually. I mean, essentially, we've got plenty of level 2 algorithms in development today that have been tested, and we have
I cannot hear you, Craig.
I'll probably stop there.
No.
Okay.
Can we continue?
Yeah. I mean, if it'll work.
Yeah.
I think it's frozen on my side. But actually, I mean, Hugo, I'm happy to stop there, to be honest, if you want. You're muted.
Hugo, you're muted. Yeah.
I mean, we can continue. If it keep working, we can go ahead.
Yeah. If you click again, will it go through? I've got the same slide, summary uncertainty modeling.
It's okay, or go ahead.
All right, I just see the same slide.
I'm passing the slides.
Okay. No, it doesn't change on my side.
I see the product simulations slide. Is that what you all are seeing?
I'm just seeing uncertainty modeling on my side. Yeah.
Yeah, we are in product simulations, science simulator.
Yeah. I don't know why it's blocked on me. Let me just try and Okay, I'll try and just.
Maybe you can try to re-enter in the session if.
Yeah. Okay. I'm back again. Yeah.
What slide what we are in the slide number 77?
Yeah, that's all right. The simulation slide. So we have an open source simulator which has been developed by Catherine Prigent and co in Paris called CEPS, and we've simulated a lot. There's quite a few papers there to look at. If you look at the next slide, Hugo, see if it'll go through. Yep. This is more or less the next animation, which maybe you have to click again here just to budget on a bit. I don't know why this one stops like that. But the idea here is that this animation will show how we can make multiple products from the same data sets. And if you click into these, I don't know if they'll work. These are showing you different orbits from different missions which work together. So Sentinel-1, Sentinel-3, Sentinel-2, the Crystal mission, the Roselle mission. And all of these different missions work in one way or another together with the CIMR, which really reinforces both the CIMR side and also the other side. So for the SAR missions, synthetic aperture radar missions, we have near full overlap for Sentinel-1 and CIMR, and Sentinel-1. And for the Sentinel-2, we provide complementary data. The next slide, please. Yeah, I'm more or less wrapping up now. I mean, product consistency is a challenge. We want to make sure that we've got consistency across all of the level 2 geophysical products. And there are different ways of doing this. But essentially, we'll try to do a multi-parameter retrieval to start with. Some products, like the CIS concentration, CIS drift, don't work in that same way. And also the soil moisture. But where we can, we're trying to use a consistent approach. And several ATPDs work together to do that, particularly in terms of the remapping and then the geophysical product extraction. Next slide. So the current schedule is we're looking at the launch of the first instrument will be in 2029, 2030. The qualification review is at the end of 2029, and we still remain on target for those dates. So we should be having some data in 2030. Next slide. Yeah, there we go. So CIMR, because of that, will be then ready for the International Polar Year in 2032 to 2033, which is going to be really useful for everyone. And that's a hard deadline for us. We want to be on commissioning in 2030 so that everything is shaken down properly by the time we reach 2032. Next slide, please. Okay, so that's just a summary and takeaway, and that's really the end of my presentation. Thanks for your time.
Thank you for this excellent talk. You have been impressive. So now it's time for questions. So people in the audience, go ahead and ask your questions and comments to Craig. There are some comments in the, maybe in the chat. We have some comments. I will check that thing in chat. Comments. Well, I have several questions. I think I have many questions. So maybe the first thing is that I think that maybe CIMR will be like will revolution their science in many ways. And also it will provide continuity to SMOS and SMAP. So I think that this is maybe the largest added value, providing continuity to SMOS and SMAP, and at the same time revolutioning many fields. So from your perspective, what is the main added value of this mission?
So, I mean, for me, it's an increase in spatial resolution with a very tightly controlled beam for the radiometer. Because if you think about small SMAP and AMSA instruments, they all have very large footprints, 40 to 60, 70 kilometers at L and C band. So while CIMR doesn't do much of a change at L band, at C band with a 15-kilometer footprint, it's almost, well, it's much better than half the size of everything else. And that's really fundamental. And then oversampling in the scan direction and in the flight direction means that we can regrid, and we're expecting sea surface temperatures of gridding to about 5 kilometers. That coupled with the very high sensitivity, in other words, the low any delta T's, 0.3 at L band, 0.25 at C band, really means we have not only a good spatial resolution, but we have a good fidelity as well in terms of radiometry. So I think that's the big leap forward. Over land, there isn't going to be a mission. There isn't another mission like this. So for the land people, this will be a bit of a step change in capability. I mean, we can do a lot with L band, but we can do so much more when you complement with C, X, K, Ka.
Yeah, I'm a land person. I'm focused now with Genesis reflectometry and on Fristo. So I think that CIMR from my future, research will be like a very interesting mission to work on. So yeah. I'm very happy to have this opportunity to analyze this data. So that's great. Yeah.
And it's all freely and open data, so there'll be no problems to get this. And, it should be straightforward.
And any plans to combine this data with maybe SAR, Genesis reflectometry of different other complementary missions?
Absolutely. I mean, with Roselle L-band SAR and Sentinel-1 C-band SAR, those orbits are both in dawn dusk. So they're the same style orbit as CIMR. And in fact, those orbits fall, the SAR orbits from those two missions fall entirely within the CIMR footprint all the time. So you'll have almost continuous microwave radiometry and L-band and C-band SAR over all services when we're making measurements. So in the polar regions over sea ice and ice sheets, this will be a real big change. And again, over the land, that will be really fantastic.
Great. I think that will be a very nice, mission for the full community. I imagine that we're going to now, dedicate some time to, for dissemination now that the mission is ready. So I think that people at IGARS and AU will be happy to know more about that mission. So that's great, I think, in general for all the community.
Yeah. We have a session at IGARS in Brisbane this year in August. So if people are there, then we'll be there. So come talk to us, and if you've got ideas you want to get involved, I mean, we're open to collaborations. We've got test data sets that people can look at, so no problems.
For sure, I'm attending IGAS and I will be very happy, and many people will be also going to attend that session. So that will be great. I think that many years working on this, many effort. So taking back in time, what is the biggest lesson learned in this process? I think that many new things, but if you can select one day or one thing that you can highlight from the full process of developing this mission.
I think you have to believe in it. I mean, you imagine when I came to the program managers here and said, I want to build this mission. It's got an 8-meter mesh rotating antenna. And they all just laughed and said, go away. You're not doing that. And it took 20 years. It's taken me 20 years to get to where we are today. Slowly, surely, both on the technical side to actually shake down all of the different technologies that we needed. And then at the same time, get a programmatic break whereby the European Union wanted to fund a microwave imager. So a little bit of luck, but sometimes you make your own luck. I mean, people don't ask for things unless they've got a good idea that there is something available. So you have to just stick to it. You have to believe in what you're doing and try to convince others that this is the right thing to do. And I think if you really believe in it and it is the right thing to do, it will happen. I mean, I always say good ideas will get money, not the other way around. Bad ideas just can get money, but good ideas will always nearly get money. So don't worry about the money. Just believe in what you're doing and keep at it, and eventually you'll get what you need.
Okay, so congratulations to you and all the team. And
I don't hear you now.
Hope to see you soon in a coming conference. And thank
Hugo?
you very much for this great talk.
There are a few questions in the chat. Okay. I know we have a few minutes
I don't
left.
Really see you.
Can you hear us, Craig?
If you can hear me, I can answer the questions in the slides. The hotspot of SMOS is Ukraine and Myanmar. That's where there are wars, and that's when there's jamming for high frequency for radars, and so the microwave images are able to see that very clearly. What spatial resolution is expected for soil moisture? We're expecting a 40-kilometer spatial resolution, which is not so far off what SMOS and SMAP do today. I think those are the two questions I have in the chat.
Okay, so any more questions? Please don't be shy and take the opportunity to ask Craig. This is a great opportunity. So if any more questions. Okay. If not,
okay. For which kind of product? Yeah, no. There's one here which is about third and fourth components of the Stokes factor. So the third component of the Stokes factor is very important for Faraday rotation corrections at L band and C band. That's necessary, but also it gives you a handle on the directional effect of wave, the surface roughness over the ocean. So from that, you can use the third Stokes to give you a handle on the wind direction. So we can get a wind vector by using Stokes. Then when it comes to sea ice, it's very tricky. It's a bit of an unknown. We've got some examples, but they're not conclusive. So we'll be looking at that. The fourth Stokes vector should be 0 unless there are non-natural signals. So the fourth Stokes is very small, but you can use it to actually understand if you've got RFI taking place in your signal. So the fourth is quite challenging. It's plus or minus 3-4 Kelvin at most. So it's quite a difficult parameter to measure. But CIMR we'll try to measure all of those on board. Certainly we will measure in HMV and we will compute then the modified Stokes vector on board. Okay. I think that's all the questions.
Okay, so maybe it's time to conclude the talk. Thanks again and congratulations. So thank you and see you soon. Bye.
Yeah, thanks, Hugo. Thank you, everybody. Thanks for the time. Have a great day. Bye-bye.